Hello class, welcome to lecture 4, in which we will take our new understanding of multidimensional linear response theory and our postulated Gaussian field theory for the density and actually get our first non-trivial or even maybe familiar to some of you results. Namely, by the end of this lecture, we'll have derived within this framework Debye-Huckel's theory for how ions distribute themselves relative to each other in dilute solutions. Before we get there, there's a couple points of order. We need to understand a little bit more the continuum limit we took at the end of last lecture, namely how exactly we should manipulate and conceive of this density field and the correlations at different points of that density field. That will require us to take a little bit of an aside on calculus of variations or functional calculus, which is just a continuum limit of vector calculus. And then, as I said, at the end, we'll be able to write down a perturbation theory on the density field, in this case, the density of ions in a solution, and derive Debye-Huckel's result. All right, so in order to get there, we need to take a few minutes to think about the density field, and its correlations. Okay, so we defined on the first lecture in motivating, or in the second lecture, motivating the statistics of density fluctuations, a little indicator function that told us how many particles were in some little volume. That idea is essentially what we're going to use in the limit that that volume is infinitesimally small. Namely, we can think of a definition microscopically of the density of a solution at some point in space R as an indicator function that asks, at that point R, is there a particle? And if I sum over all particles labeled I from, say, 1 to n, if one of those particles is at location R, so its position is at Ri, then that will return 1. Otherwise, it will return 0. It's not necessarily obvious that this definition of the density conforms to our macroscopic notion. But if we averaged it, over the course of, say, thermal fluctuations, well, averaging operation is a linear operation. It commutes with the sum. So I can bring that averaging operation inside. If all the particles are identical, so I'm working with some simple solution, say solution of argon atoms, that gives me n of the same terms. So I can tag, say, the first particle and ask for its expectation value. Now, what is that? Averaging the delta function, in this case, as typical, it has some notion of a probability. It's an indicator function. Delta functions are kind of awkward functions in that they don't look like they have units, but of course they must have units. Delta functions are defined only under the integral as 1 or 0 under that integral. So they're normalized to 1, which means that they need to be normalized by some volume element. So they have natural units of 1 per length to the d, where you're operating in a d-dimensional space. In this case, there's still an interpretation of a probability. It's a probability of the likelihood of finding a particle at that specific position, R, if we are in a solution which is translationally invariant, so that it is equally likely to find a particle at any given point in space, then the probability of finding it at one particular point is just 1 over the number of points. And we can summarize those number of points by just knowing the volume that that fluid is contained in. Again, we assume that all points are equally likely, so that the probability of finding the particle at any particular point is just 1 over that volume. A really fancy way of saying that is that the fluid has translational invariance. Therefore, N times 1 over V is what we usually mean macroscopically by the density. In this case, we'll denote that specific density, the bulk number density of the fluid, with an over bar on the row. So indeed, often we note that due to the translational invariance of a fluid, the fact that if I look at one point in a fluid or another point, statistically, those should be the same. If I have a bulk system, so I have no notion of interfaces or where the fluid ends, that just the average microscopic density doesn't contain any information about the structure of the fluid. So that's our first definition. We have a microscopic density, but its simple average is just a number. In fact, while the first moment of the density field is simple, its second moment is exactly the correlation function we've defined last lecture. So let's also define chi of R and R prime as the second, cumulant of the density, or the correlation function in the density, for the density. So that is an object that asks for how are fluctuations in rho at R statistically correlated with fluctuations of rho at R prime. We call that function a correlation function because if rho at R and rho at R prime are statistically independent, that would mean that I could average them separately. And the average of a fluctuation there, the average deviation from the mean, is 0 by construction. Okay, so it contains information about the correlated nature of the density fluctuations in our fluid. We can get some insight into it by actually introducing our microscopic definition of the density and understanding the consequences for the structure of the density correlation function. So noting the definition we had above, we can write chi of r and r prime as an average of a sum. Now I have two factors of rho. Rho is defined as a sum, so I need to introduce another dummy variable. I have a sum over I and j. Rho r is the delta function of r at less ri. So I have a delta function of r less ri times the delta function of r prime less rj. That's the fluctuation piece. And I'll have two factors of the bulk density as the average. Worth, I guess, noting that we define this, as we did last lecture, as the density less its average. Okay, now that is a definition of that chi, or it's a way of evaluating that chi from the definition of rho. We can go a little bit further. Again, if all particles are statistically the same, I can bring that averaging operation inside, like so. And I can do one more thing, which is to note that that double sum contains elements where I is equal to j and elements where I is not equaling to j. There are n terms where I is equal to j. So let's pick one of those out, in which case I'll have a delta r less r1, if that's the one I decide to pick out, and r prime less r1. That's the I equals to j term. In addition, I have n times r minus r1, all of the terms not equaling to r1. So j from 2 to n, r prime minus rj, averaged, and then our mean density squared again. Just dividing that's double sum into terms where I is equal to j and where they're unequal. Now this first term on the right-hand side is identically 0 unless r is equal to r1 and r is equal to r prime and thereby r prime is equal to r1. So I can write that as integrating over one of those r's. That delta function will give me a 1 over volume times the n out in front, returns the bulk density. R and r prime are not fluctuating variables, but still require the constraint that they are equal. So that is not an average quantity, but it is along the diagonal in this chi matrix whose entries exist along the r and r prime axes. So that's the first term. Now the second term, I can multiply and divide by the average of a delta function. One of those will give me a factor of 1 by v, times the n out in front will give me a factor of rho. The other I could keep implicit or explicit, and I'll have the delta function we had before, the sum and divide by that average of a delta function. Still have less rho bar squared. Now this term here, the middle term, that is, again, averaging a binary variable, has the interpretation of a probability. These are ratios of binary ratios of probabilities. This says, what is the probability that R1 is at R and Rj, summed over all j, is at R prime, divided by the probability that R1 is at R. That has the form of a so-called conditional probability distribution, which is equal to a joint probability distribution, probability that two conditions are satisfied, divided by a so-called marginal probability distribution, the probability that just one of those is satisfied. In this specific case, it is the, so just for completeness, one typically writes a conditional probability, in this case, B given A. So in this case, the highlighted part of the equation is given R1 is at R, what is the density at R prime? Now that is kind of ugly to look at, so typically that highlighted term is given a variable, so one can write chi R prime as this diagonal piece plus rho bar squared times a function g of R less R prime minus 1. The 1 coming from the bulk density squared we had before. That g of R is a so-called radial distribution function. Or often referred to as the g of R. And let's interrogate it a little bit. So it was defined as rho times the g of R was equal to a delta function of R1 times the sum over j from 2 to n, a delta function constraining R to be Rj divided by average of delta R1. So again, because that has an interpretation as a conditional probability, it is essentially, this g of R times rho is essentially asking what is the density at R. That would be essentially this highlighted piece, summing over most of the particles, the delta function of r less that position of those particles. That is just the density. The additional pieces, this delta R1 under the averaging operation with it, divided by the average of delta of R1, provides a conditioning. So rho times the G of R conditions the density on there being a particle, in this case R1, at some location, at this case, at the origin. So if the particles are uncorrelated, all J particles in the sum, in the highlighted sum, don't care about R1 being at the origin. This would return just the bulk density. However, if the particles are correlated, like you'd expect particles that take up a finite amount of size to be, then the density at some r away from the origin will depend, at least for some distance away from the origin, on that conditioning. Physically, you should imagine a particle sitting at the origin. At very least, other particles can't also sit at the origin. So the density field in the vicinity of that particle that's tagged and put to the origin has some different shape or form to it than it would have if I didn't fix a particle at the origin. We will, next lecture, sketch out some examples of these G's of R's for common states of matter. Indeed, at this point, we've not really assumed anything about the form or the specifics of the system. These are all just ways of characterizing a density field. But note, the correlation function for density fluctuations has a diagonal trivial piece, and all of the non-trivial structural information comes from this G of R. Okay? So those are two components of our density field that we need to know how to manipulate. We are building some intuition for. We also need to know how to perturb the fluid. So let's imagine we have a potential that acts on each particle. Let's call that potential capital Phi of R. And now let's imagine that total potential is some external potential, maybe like gravity, that acts locally on where each particle I is in space. So again, this could be some external potential I applied to a fluid. If it acts just on each individual particle, the total potential associated with the addition of this potential, the total energy associated with this potential acting on the total fluid would be just to sum up all of its components acting on each individual particle. Now, if I can express that potential as a sum of single-bodied functions that depend on just Ri individually, I can do a trick. I can introduce an integral, evaluate phi little phi not on a particle, but at the position r, at the cost of introducing a sum of delta functions with arguments r minus ri. So this is a really obnoxious way to multiply by 1. I sum over delta functions and evaluate phi at a different value, a field point r not on the particles. Again, if you did those integrals and forced those delta function constraints, you would get the line above it. But what's convenient here is the particles are what fluctuates. Phi is some known function that has some r dependence. Further, summing over all the particles, a delta function of r minus the position of those particles is what we mean by the density. So we have just arrived at a way of writing an applied external potential as a field conjugate to the bulk density. So any external potential that acts on single particles, like a gravity or some optical tweezer that's just applying forces individually to each particle, it doesn't matter where particles are relative to each other, can be written then as a linearly in the density. In this case, an integral over the density weighted by that function. So that linearity, if rho is our fluctuating variable, phi then is some perturbation we're applying to that. We can imagine turning on and applying to the fluid. If rho is like x in our harmonic oscillator, phi is like f, the force we applied to that harmonic oscillator. Now we are in a position to actually write out what we would mean by the partition function of this Gaussian density field theory. So in this case, our fluctuating dynamical variable is the density field. We have an effective Hamiltonian a way that we can assign statistical weight to each configuration of the density field, each pattern of density. And we know how to perturb it. So if we, in the presence of some external field, the partition function is an integral over all possible ways that the density field can be arranged. Think, if you want a physical picture, think about a drum. A drum has a local height field. The membrane of the drum can come in and out of plane. If I describe the field of heights of that drum, the partition function associated with that field would be looking at all patterns of different height configurations across the head of the drum. In this case, the density field fluctuates. It has all manners of fluctuations, and we need to sum over, or in this case, integrate over, all possible ways that that density field can exist to compute the partition function. In the presence of the field, we have to weight that sum by its reference Hamiltonian, which is a functional of the density. And we would have the perturbation, which we just worked out how to write. So this integration over fields is also essentially the same. It's a Gaussian functional integral. It also is essentially the same as a path integral, where you sum over all possible ways the field can be in this case. Now, if I play my same trick, there's very few tricks we know how to actually use, but if I multiply and divide by the partition function in the absence of the field, I will be, like I have been before, able to write the perturbation part as an expectation value. In this case, of an exponential of minus beta, an integral over the field weighted by the density, evaluated in the absence of the field. Where, just for concreteness, Q naught is the path integral over all possible density fields, weighted by just the reference part of the Hamiltonian. And the structure is identical to what we've seen before. Here, log of Q of phi is a cumulant generating function. It just looks a little more scary because it's now of a field in infinite dimensional vector space. Taking the appropriate derivatives, more on that in just a moment. Again, the field has components at all r. So I have to tell you which r I want to ask for the derivative with respect to. If I take the derivative of log of Q with respect to beta, the field at r, I will get rho at r in the presence of the field. If I take the second derivative at the field at r, and I'm free to take it at a different r, say r prime, that is how the average density at r, the presence of the field, changes with a field at r prime. As a cumulant generating function, this also means, minus sign, that it's the second cumulant, or in this case, the correlation function. Delta rho at r, delta rho at r prime. So in this case, the functional path integral, or the path integral for the representation of the partition function, if I take derivatives of the functional dependence of the density, so how the density depends on the function phi of r, I get information about the spatial dependence of rho at first order, and at second order, the correlations in rho. Okay, so indeed, these derivatives should look a little scary. Those are called functional derivatives. And so it behooves us, I think, to take a little bit of an aside on variational calculus and how you actually manipulate functionals and actually prove to yourself that these sorts of relationships hold. because it's likely that many of you have not taken a class in functional analysis or functional calculus. Okay, so for at least personally, the best way that I think through functional calculus is by thinking about the analog or the analogous operation in vector calculus, which I think in physics and chemistry we have more exposure to, and just trying to conceive of the limit where the number of components of that vector gets really large. So concretely, if I imagined some vector f with components f1, f2, up to fn, that's an n-component vector. If I want to know something about that vector, I have to specify which index I want to query, or I can specify which index I want to query. The analogy, so I can't write down an infinite number of components in the vector when I take the infinite limit, or I divide up these intervals infinitesimally small. So vectors map essentially to functions, where now x is a continuous variable, but it plays the same role as the indexing of a vector. So in a vector, I give you an index, that index maps to a number. A function maps an argument to a number in an analogous way. Similarly, I can construct a function g, which depends on that vector, in that I put in the whole vector, and the function g maps that function, or maps that vector to a number. G concretely could be a modulus. When I take the number of components infinitely large, let's denote this as capital G, I put in the function f. Through G, I will get mapped back a number. This is called a functional. So a operation that maps a vector to a number is a function. An operation that maps a function to a number is a functional. Okay, so I think that's all reasonably straightforward. Now let's get a little bit more complicated. If I wanted to know how the function g changes as I change one component of the vector, I could take its derivative. So specifically, I can ask her, how does g change with one component, say the ith component of the vector f? And for this to be well defined, I need to ask for that change in a specific direction of the function space. And most often, it's convenient to hold all other components constant. So holding all fj not equaling to I constant, I can ask for how does g change with fi. So that's a normal derivative. The analogous operation in functional calculus would be to ask how does the number that g maps the function to change as I change the function f at x. So to designate the difference, a difference between a normal derivative and a functional derivative, we usually use this little delta. So I can ask how does g change with a change in f. So those are derivative relationships. To understand how they work, we should think about how the arguments of the function or functional change. So if we thought about first order variations to a vector, so if I have some vector f, which has components f1, f2, up to fn, it's a well-defined question to say, first ask for small changes with respect to changes in f. So how f, if I add a little delta f to 1, could similarly add a little delta f to 2. What would that imply for how g changes with small changes to its vectorial argument? So this is the stuff of traditional vector calculus, a first order change in g due to those changes in f. Well, there's a number of different ways g can change depending on how many components of the vector there are. If there are n components to the vector, there are going to be n contributions to the first order change. Each will be weighted by how the individual component changes the function g, holding all other components constant, weighted by the corresponding change in the component. The cross terms are higher order. Those would be important at second order derivatives, as we know from vector calculus. To understand first order changes in functions, let's imagine taking our function f of x and adding to it some little delta f of x, and then asking what is the analogous change in the functional g. First order change of the functional g, delta g. playing the role of the sum that I would get in vector calculus. When I take the infinite component limit, the sum becomes an integral. So now I need to integrate over all indices, infinite indices, denoted x, how each one of those change g weighted by those corresponding changes. So then there are some simple basic rules. If g, the function, is just one component of a vector, so again, that's a map from a vector to a number. If I want to know how g changes with different components of the vector, well, in this case, it can change only if I'm manipulating the component that g is a function of. And as it is a linear function of that component, I get back a Kronecker delta. The functional g, if it is defined as the function f evaluated at a specific point, x naught, changes in g with respect to the function f, say at x prime, can only affect changes in g if x prime is x naught. So behooves us to go over a couple simple examples. Imagine I have the functional g, which is written as an integral over x, a of x times f at x. The derivative of g with respect to f at x prime is going to be integral x. It doesn't act on a of x, and I get derivative of f of x with respect to f of x at x prime. That is equal to the delta function x minus x prime. Under the integral, that delta function eliminates the integral and pulls out a evaluated at x prime. Slightly more complicated if I define the function ol, g, as an integral ax, say, times f of x minus x naught quantity squared, and ask for changes in g with respect to f of x prime. As a function of f, I get the same sort of usual chain rule that will give me twice f times x evaluated at x prime. Let's do this in a couple steps. So I can pass this under the integral independent of a. I have the derivative functionally of x prime, f squared x minus x naught. That gives me twice the integral, the derivative of f of x minus x naught with respect to f at x prime. That is the delta function of x minus x naught minus x prime. Which then evaluates under the integral a of x at x naught plus x prime. Sorry, that should be a plus, and this a minus. And then f of x prime. Okay, so I think Yoon is going to go over some more examples and some more common manipulations, but that should give you some sense for how functional, a quick introduction to functional calculus. Again, if things get confusing, turn everything into vectors, work things out there, and then take the appropriate continuum limits. Okay, so now this has been a lot of math over the last few lectures. Now let's actually solve a chemistry problem. Let's consider the following problem that Debye and Huckel did. Namely, let's imagine I have some solution where I'm going to ignore the solvent. Solvent is just imagined to be some continuum for the purposes of this calculation. We'll relax that next lecture. And in that solution, there are ions. Say one there. One here. And one there. And let's imagine that it is somewhat dilute, so they don't get really close to each other often. Nevertheless, they're ions, they interact. And let's ask the question, if I was to look at the origin, what happens if I place an ion there with respect to the positions of the other ions? How do the other ions reorganize when I drag an ion to the origin? Which is essentially asking, how do ions structure around each other? Let's try this again. So let's now let's do that in red. So the physical question Debye and Huckel were interested in is, how do ions, what are the spatial correlations of ions relative to each other in a somewhat dilute solution? We're going to address that question in this way, where let's imagine that we start with a solution where we've not conditioned any ion to be anywhere, the ions are free to move as they will, such that if I looked at the origin, so in the absence of any conditioning, the average density at that point would just be the bulk density. And now if I insist that there is an ion at the origin, I can do that by turning on the Coulomb potential at the origin, such that those ions then will feel, the density field will respond to that potential. And then I can ask, what is the density around that point given that conditioning? Which of course is related to the G of R, tells you about the correlations between ions. So Debye and Huckel originally answered this question with somewhat ad hoc approaches. They used a linearization of an electrostatic equation, Poisson's equation. The assumptions built into that linearization were not at all clear at the time, nor was it obvious why it was so successful. You all have probably heard of Debye-Huckel theory before. It works incredibly well. Essentially, the reason why it works so well is what we're going to uncover, namely, it is an application of a self-consistent linear response theory. Okay, so hopefully the setup is clear. We have a solution of ions. We're going to turn on a potential at the origin and ask, how do the ions reorganize? How does the density field associated with those ions change? The specific potential we're going to add is the interaction potential that the ions interact with, some Coulomb potential, call it U of R. And we can ask, given that perturbation, how does the density respond? So the initial bulk density at the origin will go to some conditioned density, which is characterized by the G of R. So note the way we've set up this response calculation is to start with a uniform density of ions. Ions are free to move as they like. So it's something we know a lot about. We know that lacking any conditioning, the density at the origin is just the bulk density. And our aim is then to see how the density at that point responds as we place an ion there. So this is a perturbation theory. We're going to ask only how the density responds to some linear order. And we should expect that if the field we're applying is weak, namely the ions interact fairly weakly, which would be the case if they were fairly dilute, so they don't see each other all that often, the average potential is fairly small, this should work out pretty well. This will be a pretty robust answer. You should expect, we should anticipate that in the limit that the ions interact strongly, this should break down. We should have non-linear response effects. Okay, so let's pull out the result that we know holds, namely, if we're considering linear response, we can ask for the density at R in the presence of a field. And to first order, that should be the density at R in the absence of the field, plus an integral overall R prime, how the density on average at R changes with a field at R prime, evaluated in the reference, times the field at R prime. Now, the structure of this is just our first order perturbation theory or linear response result. We have the reference density as the first term, and the functional derivative of the density with respect to the applied field times the field integrated over all points we worked out at the beginning when we were discussing the density field statistics and noting the cumulant generating function structure. This result here, that the way the average density changes with an applied field is going to be, in this case, beta times the correlations between the density, in this case evaluated in the absence of the field. That would be naively evaluated in the absence of the field, but note that we could, for example, put rho, so this is rho, field, and then evaluated in the absence of the field. We could put rho of the field back into that equation. If we did that, we would get a second integral. So we would get the first term. We'd have that term from the first term on the right-hand side of this equation. But in addition, we would have now a second integral, R prime, and now a second derivative times two components of the field. We could keep doing that, but note that if we kept doing that, we would just be generating the same sequence. Rho is equal to the derivative of rho with respect to field times the field over an integral. If we did that to infinite order, we would have had the exact rho on the right-hand side, or the exact correlation function on the right-hand side. So we would have a relationship rho of R in the presence of the field is equal to rho in the absence of the field plus integral rho, how it changes due to the field, times the field, evaluated in the presence of the field. That is to say that the self-consistent nature of linear response we described last lecture will naturally generate a self-consistency in this equation too. Specifically, identifying rho of r in the presence of the field as the conditioned density with an ion at the origin. That's rho of the g of r. The bulk, the density in the absence of the perturbation is just the bulk density. And now plus or minus beta times an integral over r chi r minus r prime. Sorry, now we put in that we're adding the potential u of r. Now chi is nothing but rho along the diagonal plus rho squared, the g of r minus 1. The self-consistency, so we have essentially a g of r on the right-hand side, a g of r on the left-hand side. If those are the same g of r's, so not the perturbative g of r on the right-hand side, we have a self-consistent expression now for the g of r. So namely, we would get rho times the g of r minus 1 by bringing this rho over to the left is equal to minus rho times, oh, not rho, sorry. Oh, yes, that's rho. So minus rho times beta u of r from the delta function in chi. And the next order term would be minus beta rho squared integral over r prime g of r minus r prime minus 1 times phi of, sorry, not phi, u of r prime. So that follows from introducing the response function chi under that integral and using one of those integrals being the delta function. Now there is a rho common everywhere, so I can take this one out, that one out, and one of those. And if I also introduce a function h of r as the g of r minus 1, we have h of r is then equal to minus beta u of r, the interaction potential between the ions, minus beta rho integral r prime h r minus r prime times u of r prime. We have a self-consistent expression for the radial distribution function less minus 1. So the structure of this, I think, is pretty interesting. We are doing a response calculation, and we're asking how does a density field respond? But we're doing it in a way that lets us actually compute what the response function is. We get the correlation function between ions in the way that we've set up this calculation, given that we can impose this self-consistency at linear response, or using the random phase approximation. Namely, that we could go to linear order in those pair interactions. And that pair correlation function, the radial distribution function, is going to be a solution that satisfies the self-consistent equation, which depends only on things like beta, the bulk density, and the interaction potential U of R. Again, U of R has shown up because that is the field we applied at the origin to cause or to promote this density reorganization. Now, note there's a little more structure to this equation. It's linear. H of R appears linearly on the left and right hand side of the equation, which means it will be solvable. And the way to solve equations like this is to use Fourier transforms. Specifically, what makes this equation not just an algebraic equation is the fact that on the right-hand side, H of R enters under the integral, but it does so in a convolution with U of R prime. Fourier transforms will decouple that convolution, making it an algebraic equation. Oh, excuse me. Okay, so let's introduce the Fourier transforms of H of R as an integral over K e to the minus I K R H of R. So we need to introduce that Fourier transform. We also need to introduce the Fourier transform of the potential U of R. Like so. If we introduce those Fourier transforms into the self-consistent equation for H of R, the convolution theorem will turn that integral of H of R minus R prime U of R prime into a product of the Fourier transformed functions. Those are, let's try that again. Those are, of course, H hat of K and U hat of K. That convolution will end up being a product H hat of K times U hat of K. So putting that in, we will get H hat, a terrible H, let's try that again. H hat of K is equal to minus beta U hat of K minus beta rho bar H hat of K U hat of K. Now this is an algebraic equation. Solving it, we get H hat of K is equal to minus beta U hat of K over 1 plus beta rho bar U hat of K. So that is a general solution. Now for the radial distribution function for this system of solutes interacting through potential U. We've actually not had to introduce anything about the ions in this case to actually note that the solutes were charged and that the potential we were envisioning to be a Coulomb potential, the only condition on the potential we've had to introduce so far is that it's Fourier transformable. We know ions interact with a Coulomb potential. U of R is equal to some z squared over R. The Fourier transform U hat of K of the Coulomb potential is well known. It's 4 pi z squared over K squared. That one is simple because you can write down Poisson's equation in Fourier space. You know that the solution to Poisson's equation for a point charge is the Coulomb potential. If you Fourier transform that with a delta function source, you will get this potential back out. The K squared just comes from the second, the Laplacian of the potential. Happy to derive that for folks in our small group discussion. Given that that's the Fourier transform of the potential, we can put that into our equation for h hat of K, and we would get h hat of K is equal to minus beta 4 pi z squared over K squared. Note, z are, I've written the Coulomb potential in units where the charge z includes the permittivity of free space or any static shielding due to the solvent. So any finite epsilon. So that's all rolled into the effective charge z. And I get a 1 plus beta rho bar 4 pi z squared over K squared. If I multiply top and bottom by K squared, I get a minus beta 4 pi z squared over K squared plus, now whatever is over on the last part of the denominator has to have units that are consistent with K squared. K, of course, the wave vector has units of inverse length. K squared, this has units of inverse length squared. So let's introduce a variable kappa squared, which also has units of inverse length squared. So a natural length scale has come out of this analysis, where kappa inverse is 1 by the square root of beta rho bar 4 pi z squared. So that's a natural length scale. We didn't have to do anything other than this algebra to get it. More on what exactly that kappa is in a second. In real space, to get h of R, we need to inverse Fourier transform h hat of K. Noting that K and R are vectors, of course. Putting in our equation for h of K, we get minus beta z squared 4 pi squared out in front, integral over k vector 1 over magnitude k squared, this length scale kappa squared, e to the minus I k dot r. Okay, so now how do we do that integral? So the canonical way of doing this is to point or to reference the vector k along r, where the vector phi or theta, the angle theta is the angle between them. And to do that such that in a normal Cartesian coordinate, that would be z. So that lets us write down in spherical coordinates an integral, the phi angle associated with those spherical coordinates will give me a 2 pi. There's no dependence on phi. There is an integral over theta, an integral over the magnitude of k. In spherical coordinates, I'll get a Jacobian k squared. I'll get a Jacobian sine theta. That is over k squared plus kappa squared. And then I can write the complex exponential as magnitude k times magnitude r times the angle between them, which I've defined as theta. And now a u substitution for cos theta, its derivative being sine theta, lets me do the integral over theta. Doing that integral, I can simplify beta z squared over 4. Nope, not 4. The 2's cancel. I get an extra 2 from that integral. I get a factor of pi. When I do the u substitution, the prefactor out in front of u is kr. So I'll get an r underneath and a k underneath. That will cancel one of those k's from the Jacobian. Evaluating the complex exponential of u at pi and 0 gives me sine of kr. And then I have the kernel k squared plus kappa squared. That is also an integral one can do. One can do it with complex analysis. There are 2 roots to that integral that are imaginary, where k is plus or minus I times kappa. Using that, otherwise you could just do that's an exponential integral one could also do. It will evaluate 2 minus beta z squared over r e to the minus r times kappa. And that is h of r. In terms of our radial distribution function g of r, that is then 1 minus beta z squared over r e to the minus r times kappa, in which we've just learned that the distributions of ions relative to each other as encoded by the radial distribution function is a screening of the Coulomb potential. So note, of course, z squared over r is the Coulomb potential in units of beta, natural energy unit. But in addition to that, we have an exponential dependence, an exponential screening. This is kappa. And so kappa inverse is naturally associated with a screening length. So we have just solved for the structure of, in this case, dilute fluid of ions interacting through Coulomb potentials. And what we found is that asymptotically, they are exponentially distributed with some characteristic scale, kappa, that came from our linear response analysis. We'll touch on this a little bit more next lecture, in addition to talking about how we go beyond dilute limits and actually consider an analogous expression for the solvent, not just the ions embedded in an implicit solvent. So more on that next week, and I'll look forward to seeing you all in the small group discussions this week.